Okay, good morning everyone and welcome to this NEASQC webinar. I'm Pascal Bernier-Bruna. I'm the communication manager for Project NEASQC. And today's topic is managing uncertainty in AI with quantum computing. And our speakers today are Vicente Moret-Bonillo and Samuel Magaz-Romero. So before we go into today's subject, I wanted to say a word about this webinar because it's one of a series. And our objectives are to help the quantum community discover and test the libraries and more generally the tools we make available, and also to get your feedback. So we've had monthly webinars for, I think it's over a year now, and until the end of the project, which is very soon in November. There will be one more webinar, but I don't have the date yet. But you can, if you go to the full list of webinars, you will find the replays because they have all been recorded and they're also on our YouTube channel. So if you want to check past topics, if you want to listen to past webinars, it's totally possible. So back to today's subject, if I can go to the next slide. Yeah, it's working. So, sorry, I need to admit someone else. So today's speakers are Vicente Moret-Bonillo, who has been in this project from the start. I remember meeting you at the very start of the project, Vicente, and he's Emeritus Professor of Computer Science at the University of Coruna in Spain. And our second speaker is Samuel Magaz-Romero. I think you joined the project more recently, Samuel, and he's pursuing his PhD in computer science at the University of A Coruña and under the supervision of Vicente, of course. So I have listed here the related publications, and the main publication is one of the project deliverables that you can find on our website. By the way, I will share the presentations with everyone after the webinar, so you will receive it. The corresponding software is also on the NEASQC GitHub, but beyond that, more or less all the publications listed under the relevant use case are relevant too. So you can go to the use case and you will find more publications. So that's it for me today. I will leave the floor to Vicente. Vicente, are you ready? Ready to share your slide?
I'm ready. If I can share my screen.
I will stop sharing mine and.
Okay. This is here. Well, I can find it. I think this is it. Can you see the screen?
Yeah, but you're not in slideshow mode yet.
Yeah. Okay, so
perfect.
Thank you, Pascal, for nice introduction of the webinar, and welcome to, ladies and gentlemen, to this exciting and amazing webinar we are going to give, which is entitled Managing Uncertainty in AI in Quantum Computing. The presentation will have two different parts. In the first part, I will talk about symbolic artificial intelligence, inaccurate knowledge, and in quantum computing, in the context of quantum computing. The second part, my colleague Samuel Magaz will give the talk, and I will give the floor to him in order to explain what we did in our lab. Specifically, we are going to talk about symbolic artificial intelligence and make a slight comparison with sub-symbolic artificial intelligence. We will deal with inaccurate knowledge, imprecision, and uncertainty. We will pass quickly through several classic models of inexact reasoning, like categorical approaches, the Bayesian approach, the certainty factors model, the theory of evidence, and the fuzzy logic. And then we will make a quantum approach for inaccurate reasoning, in which I will present our working hypothesis, the quantum model, and the results and conclusions. Well, can you withdraw the pictures of the screen, Pascal? Because I have well, okay, no matter. Symbolic artificial intelligence is different from symbolic artificial intelligence in that symbolic artificial intelligence works mainly with concepts and subsymbolic works with data. Of course, they can cooperate each other, but symbolic is a subfield of artificial intelligence that focuses on the processing and manipulation of symbols and concepts rather than on numerical data. Here we can see a very simple comparison in which the statistics are present in subsymbolic artificial intelligence and formal logic is present in symbolic artificial intelligence. When we focus now on symbolic artificial intelligence, we have to take into account that we have to know knowledge engineering. That is a field of artificial intelligence that tries to emulate the judgment and behavior of human experts given a knowledge domain. That means the construction of computational models of intelligent behavior. And this implies knowledge acquisition, knowledge representation, knowledge validation, inferencing, and advice and explanation. But when we are dealing with knowledge, we can find two different kinds of knowledge, which is declarative one and procedural the other. Declarative knowledge is the knowledge of facts, concepts, and principles, and procedural knowledge concerns how to do something or perform a given task. The concept of declarative knowledge relies on knowing that, and the concept of procedural knowledge relies on knowing how. And for the acquisition method, for declarative knowledge, we use study and memorization, and for procedural knowledge, we use practice and repetition. That gives the characteristic of heuristic knowledge to the procedural knowledge. The question is that inaccuracy is present in both declarative and procedural knowledge. And there are many causes that make it inaccuracy to appear in information. For example, it may happen that the information available is incomplete. In many cases, the information available is not sufficient to make a categorical decision. Sometimes the available information we handle is not true. The information we use is usually imprecise. Normally, the real world is non-deterministic, so general laws are not always applicable. Our model used to be incomplete. There are many phenomena whose cause is unknown. But what is very, very important is that the lack of agreement between experts in the same field is frequent. And that happens, for example, in our case, the detection and interpretation of breast cancer. When you confront the same data to two different experts, they have differences in the interpretation. All of these circumstances make it difficult to include knowledge in rule-based systems. There are several different ways to reason with inaccurate information, which is what we want. We want to make reasoning processes with inaccurate information. And we have here, it's already done, the laser. We have the classical models like categorical, probabilistic, quasi-probabilistic, that includes the concept of subjective probability, in which we find certainty factors of the theory of evidence, and fuzzy logic. And then we have here something that is called quantum models. And I will anticipate one idea, one working hypothesis. Given that quantum mechanics is universal, and given that quantum mechanics is intrinsically probabilistic, all the classical models that are defined in an ad hoc manner should be capable of being represented by quantum approaches. So that is the main idea of the talk. I will start with classical categorical model, classical approaches. In order to define a model in a classical approach, we have to define two sets, the set of all possible facts and the set of all possible interpretations. This is the domain, and we have to define a problem by means of a Boolean function that indicates whether or not a manifestation is present in my problem or it is not present. And the goal is to find a Boolean function that indicates if the interpretation is compatible with a set of manifestations. But for that, we need a third function, which is the knowledge function that relates the manifestations with the interpretations. Here in the slide, you see the overall approach. But let me show you a little example. We have a domain with only two manifestations, manifestation 1 and manifestation 2. We have also two interpretations. We have the knowledge stated in the form of production rules, and we define a problem into the domain. The problem is manifestation 1 is absent and manifestation 2 is present. So if we use the logical approach, we find a solution which is that the interpretation 1 is true and the interpretation 2 is false. That seems to work perfect, but it happens that inaccuracy appears spontaneously even when we use categorical models. For example, in the same domain that I defined before, if we change the manifestations and we say that manifestation 1 is true and manifestation 2 is false, we find two different solutions. The first one is that interpretation 1 is false and interpretation 2 is true. And the second one is that interpretation 1 and interpretation 2 are both true. So what we can be sure is that the second interpretation is for sure a solution, but we don't know nothing about the interpretation 1. In order to try to discriminate what's happening, traditionally, we use the probabilistic method based on Bayes' theorem, which gives us an elegant way to represent the procedural knowledge in terms of conditional probabilities. This is a very elegant way, but moreover, if we take into account joint probabilities, this is very useful for the knowledge acquisition process. So the problem is resolved. We don't need anything else, but not. The answer is no. The answer is no, but because when dealing with knowledge, one of the main problems of probabilistic models is their own mathematical consistency. That means that given one evidence, the same evidence points to the hypothesis and also to the negation of the hypothesis in a different way, but it points to both. And this is not always true, especially if our knowledge is not complete. To solve this problem, we have subjective conditional probabilities that has been proposed for this problem, but it doesn't work properly. Let's go a little bit further, and in 1975, the certainty factors model was published. They defined, Charlie and Buchanan defined two different measures that are the measure of increasing belief and the measure of increasing disbelief, that are considered independently if the evidence supports the hypothesis or denies the hypothesis. Both measurements have several properties. I'm not going to go through it, but they can be combined in a single unit, which is the certainty factor. And one very important property of this model that works very well in practice is that it permits the combination of several evidences in the same framework concerning the same hypothesis. And moreover, this approach is associative. Another thing that this model permits is the propagation of uncertainty, inaccuracy in the form of uncertainty, which gives us the opportunity to represent inferential circuits. Almost at the same time, in 1976, the theory of evidence by Dempster and Schaefer appeared, published in the literature. They use also two different parameters to represent inaccuracy, but these parameters are totally different than those presented by Charlotte and Buchanan. They are credibility, which is the minimum confidence we can put on a given set of hypotheses, and we have plausibility, which is the maximum confidence we can put on a given set of hypotheses. So inaccuracy is defined not as a point, but as an interval that has a lower limit of credibility and the upper limit of plausibility. The property of the measurements are the following. Credibility is between 0 and 1. Plausibility is between 0 and 1. Credibility is less than or equal to plausibility. And there are three particular cases that are credibility equals 0 and plausibility equals 1. That means that I don't know nothing at all about the solution of my problem. If we have credibility equals 1 and plausibility equals 1, I can say, yes, my hypothesis is correct. And if I found that credibility is 0 and plausibility is 0, I can say, no, my hypothesis is not correct. But credibility can be equal to plausibility. And that leads us to a single point, which can be interpreted as subjective probability. So the theory of evidence contains, in a certain way, the theory of the probability. It also can be demonstrated that it contains the certainty factors model. Let's go now to fuzzy logic. We need a fuzzy classification, knowledge representation of fuzzy concepts. We need to define a problem in fuzzy terms. We need to perform reasoning, and we need codification. And one very important thing is the classification process. Because, for example, assume that we have the set of young people. If we have a person that is 20 years old, we can say, yes, is young. But if the person is 85 years old, we should say, no, it is not, he or she is not young. But what happens if the person is 45 years old? This is a problem. He or she can be slightly young, moderately young. So this is the reason why we have to make a fuzzy classification of concepts. Then the knowledge representation is in terms of linguistic terminology. For example, project funding is adequate, whatever that means, but we had a classification before. The project staffing is small, whatever it is, and the risk is low, whatever it is. With these ideas in mind, we have to define the problem into the space of data as a crisp input into the classification representation, so that different rules at the same time can be fired, and the solution of these rules are projected on the space on solutions. And the final solution is obtained by aggregation of intermediate solutions to achieve this kind of graph we have here. But this is an area, and to find a crisp solution to our problem, we need to decodify. And we have to integrate this area in order to attain, in this case, 67.4, that can be through different methods, like the centroid, for example. Well, now that we have seen slightly the classical models, we ask ourselves the following question. A quantum approach to deal with inaccuracy? Let's see. In the resolution of a problem, the facts may be affected by imprecision, and nevertheless, we have to use the rules of the knowledge base in order to obtain valid inferences. For example, take a look to this A. This A looks like this one, but it's not the same. There is imprecision in here. We also have the fact B, and which looks like B, but it is not exactly B. And the question implies to be able to make inferences with imprecision knowledge and categorical procedural knowledge. For that, we use an inferential circuit, like this one, a classical inferential circuit, in which we define all the truth tables concerning the data input to obtain the final truth table of the response, the answer. And the next step is to translate it into a quantum circuit in which the Hadamard gates ensure the reproducibility of the truth tables that can be obtained using the previous circuit that I showed before. But if we want to work with inaccuracy, with inaccurate knowledge or inaccurate information, we need to include imprecision and uncertainty. And for that, we need to do is replace the Hadamard gates that are in the input data for different angles, depending on the degree of imprecision in the input data, or for angles included in the computing lines that perform the calculations. So with this approach, well, each angle is a rotation, of course, and this gives us the idea of imprecision and uncertainty. With this approach, we made several experiments. In this experiment, we compare the result within the certainty factors framework. We compare the results obtained by the certainty factors model with the quantum approach that give us this result using only imprecision. That means inaccuracy in data. Then we did the same using only uncertainty, meaning inaccuracy in the causal relationships. And finally, we did it all together, and we obtained this result. Well, these results are encouraging because they show that quantum approach can emulate in a satisfactory manner the certainty factors model. And that encourages us to implement the rest of the inaccuracy models for treatment from the viewpoint of the classical approach and to compare it with the quantum approximation. And now I think that I am just in time, and I will finish my talk before giving the floor to Samuel, I will finish my intervention saying that it doesn't matter how beautiful your theory is, it doesn't matter how smart you are, it doesn't matter what's your name, it doesn't matter who you are, if it doesn't agree with the experiment, it is wrong. And that's all, folks. Thank you very much for your attention, and I will give the floor to Samuel. Thank you.
Thank you, Vicente. So if you can stop sharing, then Samuel, are you ready? So
Yes.
while you're getting ready, I will tell everyone that we will send you the slides after the webinar, and we will take your questions after the presentation. So if you have questions for Vicente and then for Samuel, then we'll take them once Samuel is finished. So can you stop sharing, Vicente, please?
Yes.
I think I am already sharing my slides.
Yes, but now that's good.
Okay,
Okay.
perfect. So thank you both, Vicente and Pascal, and hello everyone. Like Pascal previously introduced me, I am Samuel Magaz Romero. I'm a PhD student in Universidad de La Coruña under the tutelage of both Vicente, here with us, and Professor Eduardo Mosqueira Rey. Today, I'm going to give you an overview of the quantum rule-based system software library that we have been developing for the project NEASQC. And so let's start with it. First, I'm going to give you a bit of context on why this library came to be. In the NIST project, we find 9 industrial and financial use cases, each of them addressing different problems. And in our case, we tackle the problem of defining quantum rule-based systems for the staging of breast cancer. One of the objectives of each of these use cases was to develop programming libraries that are open source that work in the NISQ quantum computers. For that, what we developed in our use case was, on the one hand, a software library for users to implement their own quantum rule-based systems, and on the other hand, a practical application where we use this very same library to implement an application for the breast cancer staging. Another one of the objectives of the project was to build a stronger community, for which we have been doing several dissemination activities like this webinar. And I want you to keep this in mind because it was an important aspect that we wanted to preserve when developing our library. So let's begin by addressing how these quantum rule-based systems work. Like Vicente previously explained, there are two mainly kinds of knowledge that we can find in general rule-based systems, not only quantum ones, which is declarative knowledge on the one hand and procedural knowledge on the other hand. So let's begin by explaining how we model the procedural knowledge in these systems. We are dealing here with facts, okay, the different statements that are part of our inference model of the knowledge of our system, which can be either true or false in classical systems. We have to replicate this behavior for the quantum system. So in this case, we will use single qubits to model each of the facts. In the case that the qubit is in state 0, it will represent that the fact is false, but if the state of the qubit is 1, it will represent that this fact is true. This would be the same behavior as in classical systems, but we have the advantage of the superposition that is given to us by quantum computing. So we could have a qubit, for example, in a perfect superposition, an equivalent combination of both states 0 and 1. This would represent an state, a fact, like Vicente was previously explaining, where we don't know really anything about the fact that we are dealing with. We can lean towards falseness or truthness. However, if we wanted to model that, we could also do it with another kind of superposition. For example, in this case, our fact would lean more towards being true rather than being false. And we could also have the opposite, where the fact leans more towards falseness than truthness. How do we do this? Simply with a rotation operator. In our model, the operator that we use for these rotations is a rotation along the y-axis. This operator takes as an input an angle of rotation. And how do we obtain this angle? Well, since the value of precision of our fact is defined in the range 0 to 1, we simply map this value into another range that goes from 0 to pi. So for example, if we wanted to model a fact of a perfect combination of both states like we saw before, we would simply model that 0.5 precision of the fact into a pi halves rotation. With this, we have what we need to model facts, but we also have to relate them to each other. We do this by modeling certain routines that allow us to implement the classical logical operators that are used in classical artificial intelligence systems. Here we have presented these three logical operators that you can see here, the not, the and the or operator. While there exist more logical operators, these are the most common used ones, and they can also be used to build the rest of them. So for the not operator, we use the quantum X gate, which what does is switches the amplitudes of a qubit. So it provides a similar behavior to the classical not operator. For the AND operator, we use a Toffoli gate where the two control qubits are the two facts that we want to relate with this very operator. And in the third qubit, we would obtain the value of applying this AND operator to those two facts. In the same fashion, we define the OR operator, which uses one Toffoli gate and two control NOT gates. The workflow is the same. The two control qubits are the inputs of this operator, and on the third one, we would obtain the result of applying this operator to set facts. We have done several experiments with these operators, and they all present a similar behavior, if not the exact same, to their classical counterparts. So with this, we have the model to represent facts and how to relate them. We have everything we need to represent the precedent of the rule. But now we need a way to apply an inference from that rule. So we define how to build the different rules. In this case, we use the rotation gates for both the precedent of the rule and also the imprecision, the uncertainty of the rule. Keep in mind that the rotation of the precedent may not be necessary, as it could be derived from the logical operators that we have just seen. And the uncertainty of the rule is simply a value that, for example, imagine if you have in your system a rule that says if the sky is cloudy, there is an 80% chance that tomorrow will rain. Okay, so this 80% chance represents a value that the rule may not always apply. So it would be how we implement this kind of information, this procedural knowledge, into our system. Once we have defined both of these values, we use again the Toffoli gate, the CC0, for inference. So we, again, in the control qubits, apply the values of both the precedent of the rule and the uncertainty of the rule. And on the third qubit, the controlled one, we obtain the corresponding value to applying this inference. For example, if we wanted to build a system just like this one, a very simple one with two simple rules, we would have the corresponding circuit here on the right. If you can see here, for example, we have the rule 1, okay? If A and B, then C. How is this translated into the quantum circuit? Well, we have both the rotation gates for each of the facts here. We have this Toffoli gate to implement the AND operator, and here in this qubit, we will have the result of that precedent. Once we have that, we apply another rotation gate for the uncertainty of the rule, and we apply once again the Toffoli gate for the inference of the rule, here with the precedent and here with the uncertainty on the rule. And in this qubit here, we would have the result of having applied that rule. It is the fact C that, as you can see here, is used in the routine for the second rule in this case. So with this, we have seen how quantum rule-based systems are a powerful model to represent and manage uncertainty, mainly thanks to the probabilistic nature of quantum computing itself. As you know, that we don't know exactly the state that we are in until we measure the system at the end, etc. It is like a natural match, let's say. However, it can be quite tedious to encode a classical system with its rules defined into a quantum circuit. As we have just seen, a very simple system with only 2 rules has already 9 qubits and a lot of operators. So the question that we presented was if we could develop a tool that eases this process. And thankfully, the answer was yes. The software that we have developed is organized into 2 modules. On the one hand, we have the module for the knowledge representation with all the different elements that are required to model a problem classically, with the facts, the rules, etc. And on the other hand, we have the QRBS module, which takes care of all the implementation of the quantum circuit, of executing it, and aids the user during this process. So the workflow would be as follows. On the first step, we would define the structure of our system, okay, with, like we just saw, the different facts and the operators and the rules. Once we have that, we encode into this very system the values of inaccuracy. It would be imprecision for the facts and uncertainty for the rules. And with that, we will have the classical structure. Once we have that defined, we simply use the QRBS module to implement the quantum routine automatically and execute it. And the final step would be to simply analyze the results, as the recompilation of the results of the experiments has been taken care of by the QRBS model. So let's see, sorry. Let's see how we would use this library with a very simple example. As you can see here, we have this inferential circuit. For those of you unfamiliar with this notation, this symbol here would represent an AND operator. So we would have A and B to then give X. And this symbol here would represent an OR operator. So we would have X or Z to give Y. So once that is clear, sorry, let's see how we would build this system with our library. Well, we would begin by initializing an empty system. As you can see here, there is a mockup representation on the right of the different elements that are currently part of our QRBS. Since we have just initialized it, it is empty. So we begin by asserting all the different facts into our system. As you can see, it's as easy as calling a simple method. We will do this for all the different facts of our system until we would have them all. Keep in mind that we have to add both the facts of the precedent of the rules and also the consequence of the rules. Okay, these are elements of the same kind. Once we have all the facts asserted into our system, we would simply assert the rules now. For example, we would assert a first rule for the first operator, which would be A and B, to give us X. We would do that with the following rules. And here, for example, in this last rule, you can see that we can nest these operators as far as we wanted to. So the user has this freedom to model the circuit however they consider appropriate. Once we have defined all the rules in our system, we have to aggregate them in an island. This is basically to tell the system that these rules are related to each other. But with this, we would have defined the structure of the system. With that, we go on to the next step, which would be to declare the values of precision and certainty of the different elements of our system. As you can see here, we do that with the precision for the facts and the certainty of the rules. The system structure is preserved. We do not need to modify that, and we only need to modify these values as according. With that, we have all the information needed to execute the system. That is what we do now. As you can see here, first, if we read the precision for the H fact, which remember was the last fact of our inference process, as you can see here, we read as 0 because it has not been initialized. Once we have run the system, we can read again that value and see how it has actualized. This is done automatically thanks to the QRBS model and is the use of the library. So, in summary, the library that we have developed allows for an easy management of the required knowledge elements, facts, rules, etc. It also provides an abstraction for the implementation of the quantum circuit for those users that may not be as familiar with this programming paradigm as first, but it can, of course, be accessed later on, and also enables a fast workflow to, well, define an experiment, see the results that we obtain, and then, for example, tweak the different values of precision and uncertainty to see how that affects the end result. So with that, we have presented the QRBS library, and now we will jump into the practical application that we have developed. In this case, we have developed an application for the aid of the staging of invasive ductal carcinoma. As you can see here, it is the most common type of breast cancer, and about 75% of all breast cancers are of this type. We chose this problem on the one hand because of the previous experience of the group with this problem, but also because of its relevance in today's society. So for modeling this problem, we have used the TNM staging system, where we have different variables that relate to this diagnosis, which are grouped into the three topics that you can see here. They could be related to the tumor, related to the nodes, and related to the metastasis. Each of these groups have different kinds of variables that would have these inaccurate values according to, for example, the diagnosis of two different medical experts, okay, that with the same patient, they may reach different conclusions, and we would, for example, average their diagnosis to obtain an inaccurate value. We would use the expert knowledge to extract the different rules and the facts that are used in these rules. For example, here we have the information that describes the stage 1 of IDC, and in particular, a substage of in this case. In bold, you can see this description of stage 1A, from which we extract a simple rule, the one that you can see below. So, well, we deal with different facts like the size of the tumor and the affected lymph nodes to infer whether a stage is possible or not. However, keep in mind that there are several stages that could be simultaneously possible, which is why we want to model this problem with a system that allows us to implement inaccurate knowledge. So once we have that, we simply define an API that users can implement on their own. That basically what asks from the user is the different values of inaccuracy for the variables according to the TNM staging system. And once the user runs the the request, they obtain as a response the different stages of IDC and their grade of viability. Let's put it that way, like how certain the system is on diagnosing each of the possible stages. And all of this is implemented in quantum computers, but the user does not need to know, if they don't want to, if they don't have the time to learn it, as it is run on a quantum computer completely underneath and invisible to the user if they don't want to delve into that. But of course, they could obtain the corresponding quantum routine and analyze why the conclusions that have been returned are derived. And with that would be my part. So thank you all for your attention.
Thank you very much. Thank you very much, Samuel, and thank you for being right on time. Wonderful.
I tried my best.
Okay, so it's now question time. So I will share my screen again. Here we are. And so if you have questions, you can either raise your hand or put your question in the chat. It's whichever you prefer. So, oh yeah, I see one raised hand. Who is raising their hand? Sorry, I can't. Yeah. Question from Michael Walker.
Yes, thank you both for interesting presentations. To both of you, but maybe more it's relevant to Vicente. Have you considered incorporating Judea-Pearl's causal calculus? So you're already handling probabilities and conditional probabilities and so on in various forms. What his framework allows you to do is to expand on that and make causal inferences. So well, you haven't done it yet, apparently, but is that something you might be interested in doing going forward?
Vicente? Vicente, we can't hear you.
Space. Yeah. Hello, can you hear me?
Yes, yes, we can hear you now.
Well, can you repeat the question again, please?
So given that you're incorporating probabilities in your work already.
Because I am having problems with my microphone. And let me check.
Michael, do you mind writing the question in the chat?
Okay, I'll do that.
Sorry about this.
It's okay.
Can you hear me now?
Yes, we can hear you,
Yes.
Vicente.
Oh, okay, okay.
So given that you're using probabilities, are you familiar with them? Might you consider using Judea-Pearl's causal calculus, which sort of extends on probabilities and allows people to make inferences about causality?
Yeah, this is true. I mean, probabilities for me are a strange thing. For me, probabilities is I mean, I was shocked when I saw that the same evidence can support simultaneously to a hypothesis and to the negation of the hypothesis. This is in mathematical terms perfectly correct if we work with data. But knowledge is a kind of different thing. And having into account that knowledge is, as I said before, incomplete and inaccurate by nature, you cannot apply a strict probability theory in order to find a conclusion. So we have to manage with that because knowledge is completely different to probabilities. And there is also another problem, which is concerned to the relationships between two different facts. If we have A implies B, I said in my presentation that we can represent that as a conditional probability, which is not exactly true. I have to say that this is not exactly true, but it works.
Okay, thank you.
Okay.
Thank you.
Thank you, Michael, for your question. Do we have another question? No, if not, I have a question of my own. I have a question to, I think it's to Samuel. It's about the results of the IDC application. How accurate are they? Because, I mean, we're dealing with people's health, you know, so.
Yeah, we don't want to be wrong about that.
Yeah.
Well, as far as we have been able to test with different online systems that are currently available, since these systems do not deal with inaccurate knowledge, we could only test our system without dealing with inaccurate knowledge. And for those cases, we obtained a 100% match with these systems. So with this, we have proven that the rules that we have implemented through a quantum routine are in fact correct. Beyond that, the experiments that we have conducted with inaccurate knowledge have given us results that are coherent with what we expect. For example, if without inaccurate knowledge we obtain, for example, like we saw in the slides, a 1% of probability of the IDC being stage 1A, if we slightly varied these precision values for that diagnosis, we would still obtain, for example, a stage 8 with a 0.8 rather than 1, and another of the possible stages with a low probability too. So the idea is that here we would require the knowledge of medical experts um, that evaluated how good is this variation when we introduce inaccurate knowledge. But so far, the results that we have obtained are well, satisfy our hypothesis, the expectations that we initially had.
Okay, well, I guess that's the best we can
Yes, so far
expect today.
it is.
Okay, there is a question in the chat.
There's a question, yes.
Yeah, I will read it for everyone. I have a question about speed. Does the quantum implementation provide any advantage over the classical models? Who takes this one, Vicente?
Yes, I will take this question. Well, if you remember the age of the ENIAC,
That was a long time ago.
was big enough to perform very few calculations. And it expends a lot of heat. We are in the NEASQC area, which is something similar to the ENIAC area. So the question, after benchmarking of our system that we just finished last week, works qualitatively in the same way that classical models, but in a quantitative way, we need more qubits. We don't have enough qubits to perform calculations faster than big mainframes of computers or big stuff. But I will tell you the history of the positron. When Paul Dirac was trying to unify the theory of the relativity with the quantum mechanics, he had to put into the equation of Schrödinger a term that means a positron, which was an electron with a positive charge and the same mass of the electron. Nobody believed on that. Nobody believed on that. And now positrons are being used in order to detect cancer, for example, through the PET, is a technique. So it's a matter of time. It's a matter of time. I am sure that the real thing will be when classical computing and quantum computing cooperate in order to work each of the techniques in the field which is more comfortable for them. If we have to make calculations, we use an approach. If we have to make other calculations, we use another approach. But we do not discard at all. We don't say A or B. We say A and B depending on the problem we have. And the cooperation is fundamental, but we need still more qubits.
I would like to add a few notes to that response. In the first case, we are limited by the number of qubits, of course, and we have not yet been able to showcase the advantage of the purely quantum capabilities of this model. Like, for example, with the different inference operators, we are creating an entanglement between the precedent of the rule and the consequent of the rule. This is a behavior that provides a new way of representing inaccurate knowledge, which was the main objective when we started this work. So while that does not yield any advantages right now, we can only wait to see how that would behave when we have quantum computers with more qubits, like Vicente said. On the other hand, we are also currently developing some other models that are not so direct translation from the classical models, but rather new interpretation of how we could implement these systems with a more directly quantum approach. And in this field, we're still working on it, but we are using some techniques like the quantum accelerated Monte Carlo, for example, which are yielding favorable results. We are still have some more work to do to see where that will lead, but so far that is one of the techniques that would provide a quantum advantage over classical methods.
Let me
Okay,
finish with one
thank you.
example. With one example concerning what you said. Assume that we are working with this machine, this IBM machine that wins Kasparov playing chess. We can say that the machine is clever than Kasparov, but this machine is unable to clean a dish, to wash a dish, or to make food. So each technology has its own area of application.
Okay, thank you, Vicente. Any other question? Okay, wait. I think we have time for one last question. So I have one more. How does the QRBS software deal with large-scale problems? Do you need more qubits here too?
Well, of course, we will all benefit from having more qubits in our quantum computers. Sadly, that won't be the case for the at least near future. So what we use here was to apply that concept that I glanced over very quickly of knowledge islands. This concept allows us to divide the complete inference circuit that we have classically into different parts, and each of these parts could be executed separately on a quantum computer. We would take the result that we obtain and use that to initialize the corresponding value in another knowledge island. So we have this strategy that, maybe for example with distributed quantum computing could benefit from it, but that is the best solution that we have achieved so far, to split the classical inference circuit into different parts in order to run each of them separately and then aggregate them for the final result. So as long as you don't have, for example, a deeply nested precedent in a rule, for example, or things like that, there should be no problem with dividing the problem for it to be able to run from small to large quantum computers.
It is important to say in this point that knowledge islands are not the same thing than knowledge bases.
Yeah, no. Knowledge base would contain the entirety of the facts of the system, and knowledge islands are aggregation of those elements that from a knowledge
Special
base.
connections between those.
Exactly.
Thank you very much, Samuel and Vicente. So any other questions, or can we close for now, because it's almost time? Vicente, Samuel, is there anything you wanted to add?
Yes.
Yes, go on.
Thank you, everyone.
Well, I would like to thank everyone for their attention too, and
Okay.
also remind them that if they want to try with the software that we have just showcased today, it's available in the GitHub of the project. And if you have any more questions or doubts without it, we are here to answer them.
Okay. Well, thank you very much. So thank you, Samuel and Vicente, for sharing your findings and your knowledge. And oh, there is one raised hand. Sorry. Who raised their hand? No, must have been a mistake. Okay. Yeah, I was thanking our audience for being here today and for staying until the end with us. So you will receive the link to the slides, and the recording will be on our YouTube channel. So you can listen to it again or share it with colleagues and friends. Thanks, everyone. Bye-bye.
Thank you.
Everyone, bye.
Bye-bye.